already when we cover? Like which units?
It'll be 2.6, which was the transformations of functions. 2.7, which was the combining functions, so adding, subtracting, multiplying, dividing, doing composition. 2.8, which was one-to-one and inverses. And then the stuff we've been doing with the polynomial stuff. So 3.1 was the quadratic models. 3.2 was polynomial functions, which we just finished up. What was 3.3? 3.3 was
Dividing
no, thank you. Doing long division, thank you. And then the 3.4 and 3.5, which we're going to be talking about finding roots. Thank you, Logan. Appreciate that. I have a review sheet that I'll give out at the end of class today as well. And there's an additional one on Google too. So 2 reviews as well. Other questions? All right. Well, we started talking last time about doing complex number arithmetic because we're going to find that some of our polynomials will have complex zeros. So we'll need to do some of the computations with them. So last time we talked about how we add, how we subtract, and how we multiply. And we said for each of those, it was a lot like what we do for polynomials, right? The only thing we have to worry about is if we come up with an I squared, what is I squared equal to? -1, right? So anytime you come across an I squared, you change it to a -1, right? All right, so what we did not talk about last time was division. Division, we use what's referred to as a complex conjugate. You might have done conjugates before. If you've rationalized denominators, it's the same concept. When you do a complex conjugate, all you do is you change the sign in the middle. So if you have a plus bi, its conjugate is a minus bi. All you do to get the conjugate is change the sign on the imaginary part, not the real part. We just change the sign on the imaginary part. Let's see why we might want to do that. If you take a plus bi and multiply it by a minus bi, what do you get when you multiply that out? Not a trick question. What do we get when we multiply that? Oh, so what do we have to do? We're going to FOIL it, right? What do we get? A squared, and then we get a negative ABI and a positive ABI and a negative B squared I squared, right? That's just doing their distributions, right? Okay. What happens in the middle there? They cancel out, right? These go away. What did we just say a minute ago that I squared was equal to? -1. So this changes to a squared plus b squared. Notice that all of the i's went away, right? This is a real number. No imaginary part at all. So when we take a complex number and multiply it by its complex conjugate, we get a real number. No i's left. Okay? So this is exactly the principle that we're going to use to divide complex numbers. The idea is to get the complex number out of the denominator. So we're going to multiply top and bottom by the same thing, so that when I multiply on the bottom, I get rid of the imaginary term. Well, we just said a minute ago, when we multiply by a complex conjugate, the imaginary term goes away. So in this one, we'll multiply top and bottom by 6 minus 2i. Notice that this is going to multiply the same way every time, right? We'll get an a squared plus the b squared. The i's go away. I mean, if you need to do the distribution every time, that's fine. But what's playing the role of a here? And what's playing the role of b? 2, right? So on bottom, you'll just get 6 squared plus 2 squared. That's the whole point of doing this, is make the I term go away. Okay. Like I said, we just did it in general over here, right? We just need to identify what the A and the B are. What do you get when you distribute the top? When you distribute that 2i through, what do you get? Yeah, 12i minus 4i squared. And we just said a second ago, what can you replace the I squared with? -1. So on top we'll get 4 plus 12i, because that I squared will change that minus sign to a plus. And on bottom we get 36 plus 4 is 40. Notice that the I term went away. We also talked a little bit about last time about writing a complex number in standard form, having the A plus the B times I. If we want to do that here, I can split up the fraction into two pieces. So I'd have 4 over 40 plus 12i over 40. And then notice that those fractions reduce a little bit. What does 4 over 40 become? 1 over 10. And 12i over 40 becomes, 3 over 10 times I. Good. So this simplifies into this standard form. So notice it's A plus BI again. But this is the technique if you want to do complex number division. So let's do the next one here together. If we want to get the I out of the denominator, what do we need to multiply top and bottom by? 3 plus 9i, good. Again, the complex conjugate, literally just take the sign on the imaginary part and flip it. Don't touch the real part, just the imaginary part. And again, the reason why we do that is because it makes the denominator a real number. The imaginary goes away. What do we get on bottom when you multiply out those two complex conjugates? 3 squared plus 9 squared. Again, we have A plus BI times A minus BI. It's A squared plus B squared. Same way every time. What do we get on top when you multiply it out? -15. There's a plus 54i squared. What else do we have? Where did that come from? You're right.
-45i plus 18i.
Good. We gotta FOIL it, right? -5 times 3 gives the -15. -5 times the 9 gives you the -45i. 6i times 3 gives you the 18i. 6i times the 9i gives you the 54i squared. Again, we multiply them just like we do for polynomials, right? There's no difference in the multiplication. What do we get on bottom? We get 9 plus 81 is 90. Jasmine just said that the I part simplified to -27i. What about the parts that don't have i's in them, the real part? I squared again is equal to -1. So this becomes -54 minus 15 gives you -69. Again, this part right here is -54, right? Because it's I squared is -1. And then again, if we want to put this in standard form, we split it apart. There's a 3 that goes into top and bottom in the first part. So you get -23 over 30 in that first fraction. There's a 9 that goes into top and bottom in the second part. And so we get -3/10 I for the second part. What questions do you have on those? Same process every time. If you're asked to divide complex numbers, that's what you do. Multiply top and bottom by the conjugate and simplify. It's the only real difference of doing anything with division. The addition, subtraction, multiplication, you do the exact same things you would do with polynomials. The only thing that's a little bit different is when you hit I squared, you get -1. All right. Again, the reason why we did that little bit of a review with complex numbers is because we're going to see complex zeros in our polynomials. Again, the whole reason why you start by defining the number I is to try to find a zero of the polynomial x squared plus 1. Right? X squared plus 1 has real coefficients, but we still got imaginary numbers for solutions to the equation x squared plus 1. So that was why we did that little bit of review. So the rest of this section and going into the next section is all about trying to find zeros, whether they are real numbers or complex numbers. So we have to try to figure out some ways to help us hunt for these things. So one way to do that is what's known as the rational zeros theorem. So we have a polynomial. Remember when we have those little a sub whatevers, those are just the coefficients. Looking at that, what would be your leading coefficient? A sub which one? Which one would be the leading coefficient? What's the highest degree that you see? N, so what's the leading coefficient? A sub n, right? That's the leading coefficient, this one right here. What's the constant term? A sub 0, right? It's the one without the x's on it, right? The reason why I'm reviewing that, besides the fact that you need to be able to identify those, that comes up in this rational zeros theorem. So when you have a rational zero, remember a rational number just means a fraction, right? One integer over another one. The root word for rational is ratio. Okay? So we have a ratio of integers when we're talking about rational numbers. If it's a rational zero, then it has to have the form P over Q. Where P is a factor of the constant term. And Q is a factor of the leading coefficient. If it's going to be a rational zero, then it has to have this form. The numerator of the zero divides the constant. The denominator of the zero divides the leading coefficient. Okay. So let's look at this next one. This is the first example that we have here. This one's not asking us to find them. We'll talk about finding zeros here in a minute. This one's just asking us to list what the possible ones are. So what's your constant term in this case? The 25. So we want to see factors of 25. What are those? Yep. And what else divides 25? The 5 does, right? What's the leading coefficient? 8. What are factors of 8? Good, 1, 2, 4, and 8, right? That's the only things that divide 8. So this is going to be the first step. When it asks you to list the possible rational zeros, you want to find your factors of a constant, find your factors of the leading coefficient. So then your possible rational zeros are, well, these are your possible numerators. These are the possible denominators. So what fractions can we form? Well, I'll start with the 1. You can make a 1 over 1, which is just 1. A 1 over 2, which is a half. 1 over 4, which is a quarter. 1 over 8, which is an eighth, right? That would just be the numerator of 1 and the denominator of the other 4. What other fractions can you make? You're going to make a 5. What else can we do? 5 over 2, 5 over 4, and 5 over 8. Using the 5 as a numerator, right? That's an ugly looking 5. And then finally, what are the other ones we could make? Good. Now, one last little bit of this is that, notice I said the rational root there said the numerator needed to be a factor of the constant and the denominator had to be a factor of the leading coefficient. Well, notice that, say, for example, I can divide 4 by 2, but I can also divide 4 by -2, right? -2 would still be a factor of it, okay? So with all of these rational zeros, you can have plus or minus all of them, right? So those are the other possibilities. It could be the negatives. So one shorthand way to write that would be to put a plus or minus around this whole thing. Now the good news is that we're going to have other ways to help us check to see which ones we should actually look for. Because right now, notice that list is 24 numbers long, right? I don't think I want to check all 24 of them. That would take a while. Okay. But this is the possible list. Is this okay? Let's do the next one. Same idea. What two numbers do we want the factors of? Okay, 24 and 42. Which one is going to give you the possible numerators? Which factors are going to give you the possible numerators? The 42, right? The constant term gives you the possible numerators. The leading coefficient gives you the possible denominators. Yes? You could use a negative because we're at the end of it, we're going to do plus or minus. Yeah. So you could do -42, but remember we're always going to have plus or minus for all of them, so it doesn't matter if you put the negative. That's a good question. That's why I ignored it. Okay. What are your factors of 42? 3 goes into it 14 times, and then 21 times, and 42 times. Sometimes it's easier to pair them up, right? 1 goes with 42, 2 goes with 21, 3 goes with 14, 4 doesn't work, 5 doesn't work, 6 goes with 7, and you're done, because you got to the middle. All right. What about 24? Good. And again, sometimes it's easier to meet in the middle. 1 goes with 24, 2 goes with 12, 3 goes with 8, 4 goes with 6, 5 doesn't work, so you're done. All right, so possible rational zeros then. Remember, it's going to be plus or minus all of them, right? So I'll just put that out in the front and then put the rest in like a set. It's a little bit of a shorthand notation to do it, so I don't have to write plus or minus this and then plus or minus, and so I have to write that plus or minus every single time. What fractions do you get? Good. Yep, that's the first row. Yep, I agree. Next one. Yeah, 2 over 2 is 1. I've already listed it, right? The next one is 2 over 3. The next one would be 1/2, which we've already listed again, right? So I don't need to do it again. 2 over 6 is 1/3, which we've already listed. 2 over 8, which is 1/4, which you've already listed. 2 over 12 is a 6, which we've already listed, and 2 over 24 is a 12, which we've already listed, right? You don't have to list the repeats. Okay? It saves a little bit of writing, because there would be a lot of these things, right? What about the next ones? I think that's it for the 3, isn't it? 3 over 1, 3 over 2, 3 over 3 is 1, which we've listed. 3 over 4, 3 over 6 is a half, which we've listed. 3 over 8, 3 over 12 is a quarter, which we listed. And 3 over 24 is an eighth, which we've listed. What about the next ones? 6. So 6 over 2 is 3, which is listed. Yep. 6 over 3 is 2, which is listed. 6 over 4 is 3 halves, which is listed. 6 over 6 is, which is listed. 6 over 8. 3 over 4, which is listed. 6 over 12, 1/2, and 6 over 24, quarter. Those are all listed, right? By the way, if you go through these and you list them twice, it's okay. It doesn't hurt. You just don't have to list them twice. Okay. The next one will be notice that 7 doesn't have anything in common, so those will be different ones. Those will be new ones. Do the same thing with the 14. 14 over 2 gives us 7, which is listed. 14 over 3. 14 over 4 gives you 7 halves, which is listed. 14 over 6 is 7/3. 14 over 8 is 7/4. 14 over 12 is 7/6. And 14 over 24 is 7/8. Or 7/12, sorry. Doesn't matter, it was listed. Because we had common factors, right? Is this process okay? Making sense? I mean, this is long, but so then 21 over 2, 21 over 3 is 7. That's just listed. 21 over 4. 21 over 6 is 7/3, which is listed. 21 over 8. 21 over 12 is 7. What did I say? Did I say the wrong one there earlier? 21 over 6 is 7 halves. Then we had 7/3. And then 21 over 24 is 7/8, which is already listed. Then 42. But 42 is going to have something in common with all of those, right? 42 and 2 is 21. 42 and 3 gives you 14, and so on up the line. I think we're done at 42 at that point. Does that make sense? That's how we create them. I know that was a long one, but does that process make sense what we're doing? All right. So we're going to put these things together to help us find all the zeros. So that's what we're going to be doing in these next couple of sections, is finding all the zeros. Our goal with finding all the zeros, by the way, in every single problem, will be to try to reduce the polynomial that we have down to a quadratic. Once we get to a quadratic, we can always use what to find the zeros of any quadratic? What formula do you know that uses you can find those zeros for any quadratic? Quadratic formula, yeah, exactly, right? We can always use the quadratic formula, right? So our goal will be to knock down our degree until we get to quadratic, and then use quadratic formula or factor, one of the two. Okay, that's our goal. Right now I've got a third degree polynomial, so I need to figure out a way to knock things down. So that's what our rational root theorem is going to help us do, is to knock these things down. What two numbers do we need to figure out, or excuse me, do we need to use to figure out the possible rational zeros? 8 and 3. Constant and leading coefficient, right? Those are the first two numbers we're going to pull off and figure out those factors. What are the factors of 8? Good. The factors of 3 are 1 and 3. This will be a lot shorter list this time. Okay? So now we want to get our possible rational zeros. We can always do plus or minus, right? What are they? 1 and 1/3 and good. Good. 8 and 8/3. Good. Are we okay with creating that list? Yeah? Okay. All right. So now we want to figure out which of these might work. Okay. So I don't think I want to check all of them. That'd be a long list, right? Because there's 16 numbers, right? There's 8 positives and 8 negatives. I don't want to start doing guessing and checking to figure out which one might work. So instead, what we're going to do is go use a graph, and I'm going to use a graphing utility online here called Desmos. Yeah. Nice little thing. Okay. So let's type this in. If I can get a keyboard to pop up or not. I'll just attach my keyboard back on then. All right. So 3x cubed minus 11x squared minus 6x plus 10. All right. Oops, well, thank you. Why did I get a 10? Don't know why I put 10. All right. Notice that we see this thing on here crosses the x-axis 3 times. Again, if it's going to be a rational zero, it needs to be one of our list. Well, -1 was definitely in our list, right? Or that's 2/3. That was in our list. And 4 was also in our list, right? Well, let's check them. Just because it looks like it goes through those points on a graph isn't a guarantee. But let's check one. I'm going to use -1 because that's the easiest one to start with computations, right? Okay. So let's go back over. And by the way, on an exam, I will give you the graph, so you don't have to try to get it graphed on a calculator or something. I will give you the graph in case you don't have a graphing calculator. It wouldn't be very fair. I'm not going to expect you to go out and buy one. Okay, so I will put the graph on there for you. All right, so we can check if it's a zero by doing synthetic division. And that was why I chose the -1. It's a lot easier to multiply by -1 than, say, 2/3, isn't it? At least I think it's easier. All right. What do we do for synthetic division again? What do we do first? Drop the first one and then multiply and then the other way. Add them, yep. And then multiply and add, and then multiply and add. So is -1 a zero for certain? Yes. What tells you that it's a zero? The zero is 0. Yeah. Remainder is 0, right? So I got a remainder of 0. That tells me I really do have a 0. Right? We agree? Okay, so far we have 3x cubed minus 11x squared minus 6x plus 8 is equal to x plus 1. Remember, x minus the 0 is the factor. What's the remaining piece? What's the quotient going to be? 3x
I mean, just
squared. Good. Yep. Remember, it always drops by 1 each time. 3x squared minus 14x plus 8. Yeah. Good. Now we have this down to a quadratic. Right? We now have a quadratic. So either it'll factor, or you can use, if you can't see how it factors, you can always use quadratic formula. This one does factor. How did I know that it factors as 3x minus 2 times x minus 4? Well, on the graph, what did we find for zeros when we looked at the graph a minute ago? Flip back over to the graph. What did we find for zeros? Yeah, 2 over 3 and positive 4, right? If 4 is a 0, what has to be a factor? X minus 4, right? Then the other one would have been at 3x over 2. Does that give you a 2/3, by the way, when you set it equal to 0? Yeah. Okay. So your zeros here are -1, 2/3, and 4. And we factored the polynomial completely. This is as good as we can get. Again, notice that our goal was use the rational zeros to get this down to a quadratic, then either factor and use the quadratic formula, one or the other. Okay? Let's do another one. We have another cubic here. How many zeros do you think we need to find before we get down to a quadratic? Just one, right? Because we have a cubic, we find 1 0, that'll get us to a quadratic next, right? And then from there, we can always use quadratic formula or factor. What numbers do we need to look for the factors of? Yeah, 14 and 4. Factors of 14 are 1, 2, 7, and 14. Right, 1 and 14, 2 and 7. Factors of 4. 1, 1, 2, and 4. What are your possible rational zeros then? Here's a 1, 1/2, 1/4. What are the next set? Yeah, 2. 2 over 2 is 1. 2 over 4 is 1/2. So we already had those. Next ones. Good. And the last one. And I think that's it, because 14 over 2 is 7, and 14 over 4 is 7/2, which you already have listed. Okay. Again, do you want to check 16 numbers? No. Okay. That doesn't sound like fun. So let's use a graph again. Go back over to Desmos here, maybe. Let's click that one out. 4x cubed minus x squared minus 22x minus 14. Again, I want rational zeros, right? So that's -7/4, -1 3/4. This one is not something that I recognize as a rational number to start with, and then this one is maybe not something else I recognize right off the top either, right? So I would use -7/4 to start with, just because that's not one that I recognize off the top of my head. Okay, does that make sense why I'm doing it this way? All right, trying to figure out ones that I actually know to plug in. Okay. All right, so let's go back over. In this case, again, I only need to find one, right? Because then I can use quadratic formula past then. All right, so let's do -7/4 down here. first step is to write down the 4, and then we multiply. What do you get when you multiply those two things? And then we add to get -8. Multiply, we'll get 14, right? Because you'll get the 8 will go into the 4 2 times. So you get 2 times 7 is 14, and it's positive. If you need to use a calculator, please do, right? Add, we get -8. I bet you know what this answer is over here then. 14. We just did it, right? And then add down, we get 0. So is 7/4 -7/4 is 0? Yeah, good. Right? So again, if we think about the factoring part, so far we have 4x cubed minus x squared minus 22x minus 14. X plus 7/4 is one factor. What's the quotient? Good. 4x squared minus 8x minus 8, right? We agree? Because those, again, we went from a cubic to a quadratic, and then these are the coefficients here. Let's set it equal to 0. Again, you should always try to factor it if you can. I can factor a 4 out. But does that x squared minus 2x minus 2 factor? No, it doesn't factor, right? At least not using integers. So we can use quadratic formula. What is quadratic formula again? Good. So looking at, all I need to look at is this piece right here. What's b? -2. So we get 2 plus or minus square root of 4, because -2 squared will give me 4, minus 4 times, what's a? And c, -2. So we get 2 plus or minus -4 times the -4 will give me a +8. We'll get square root of 12 over 2. Twelve is 4 times 3, so I get 2 plus or minus 2 root 3 over 2. Your 2's will cancel everywhere, and you'll get 1 plus or minus root 3. So your zeros here are -7/4, 1 plus root 3, and 1 minus root 3. Yes?
So if we don't get a 0 from the synthetic division, then we have to try a different one?
You have to try a different one, yeah. But if you look at your graph and pick correctly, then you shouldn't have to worry. It should be the 0 that you're looking for. Yeah. This one okay? All right, let's do one of these that has a quartic, a 4th degree. So this, we start with a 4th degree polynomial. How many zeros do you think we need to find to get down to that quadratic? 2 to get down to the quadratic, and then we'll get 2 more, right? Okay. Again, our whole goal is to try to knock this down to a quadratic. So we want to find 2 to start with. To get our list of possible rational zeros, what 2 numbers do we need factors of here? 72 and 1. Good. Factors of 1. 1. That one's easy, right? Factors of 72. 1 and 72. Yep. 3 and 24. 4 and. Good. 6 and 12 and then 8 and 9 work, right? So 12, 18, 24, 36, 72. Woo, lots of them. All right? 72 has lots of factors. Again, the way to check factors is, does 1 work? Does 2 work? Does 3 work? 4, 5, 6, until you get to a pair and you run out of places, right? Meet them in the middle, right? Try 1, 2, 3, 4, 5, 6, 8, 5, 6, 7, 8. 8 makes the 9, so you're done. You get 8. Right? And again, use your calculator. Don't fight it. All right. What about your possible rational zeros then? Good. Your denominator is 1 all the way across, right? So you just get plus or minus all those factors of 72 that we had. So now let's go get a graph. Maybe. Oops. Back over here. If my mouse will work. Oops. X to the 4th. Minus 2x cubed. Plus x squared. Minus 18x. Minus 72. I don't need to go find all of them. How many do we say we need to get to be able to knock it down to a quadratic? 2. How many do you see on your screen right now? 2, right? What are they? Negative 2 and 4, right? We don't need a fancy graph. We just need a couple, right? Okay. Negative 2 and 4, we said work. All right, so let's go over here. Let's use negative 2 to start with. 1, negative 2, 1, negative 18, negative 72. Bring down the 1. Multiply, we get negative 2. Add, we get. Multiply, we get. Yeah, it's 8. And then add, we get 9. Multiply. Good. Add. Yep. Multiply. 72. Add 0. We're reading it off the graph. If we've selected properly, we should get a 0. So if you're confident you got the right one off the graph and you don't get 0, go back and make sure that you did your arithmetic correctly. All right. We started with what power? 4th. This should be 3rd, right? So let's do the synthetic division for the other 0 on this one. Okay. We said the other 0 was 4. Bring down the 1, multiply 4, add 0, multiply 0, add, multiply 36, add 0. So 4 was also a 0, right? We agree? Are we okay with this process that we're doing here? Right? Went to the graph, saw this was a potential 0. Check, hey, it really is a 0. Do it again for this one. Got that one was a 0 too. Right? We started with a 4th degree. This is now 3rd degree. This is now 2nd. All right? So what polynomial is left here? What equation do we end up wanting to solve? What is left out of this? X squared plus 9, right? We agree? Okay. You could use quadratic formula on this if you really wanted to. It's probably easier just to solve. Move the 9 to the other side. Take your square root. Remember, don't forget when you take the square root of both sides, you get plus or minus. So we have plus or minus the square root of negative 9. Now that we've introduced complex numbers, negative 9 is the same thing as what? 3i, right? Remember, the negative under the root tells you get an I. Square root of 9 is 3. So we get plus or minus 3i here for these. So we have 4 zeros, which is not a surprise because we had a 4th degree polynomial. They are negative 2, 4, and I'll write it out. 3i and negative 3i. Questions on that one? All right. So notice again, the next one would just be doing a cubic like we did before. We've got a quartic in the number 7. So again, you'd be looking for 2 zeros. There's another cubic. You'll be looking for 1 0. There's a cubic. Let's see if I can find another one here. There's a 4th degree. I mean, what was it? Oh, there we go. Let's look at this, the very, very last one. I'm not going to go through it because we only have a few minutes left. Or we'll do the whole thing. But notice that we have a 5th degree polynomial here to start with. Again, our goal is to try to get it down to a quadratic. So how many zeros do we need to find to start with? 3, right? So again, if we make our list of our rational zeros, I need factors of 20 and factors of 7. What are your factors of 20? Good. Yeah, because 1 and 20, 2 and 10, 4 and 5. And again, if you think of that meet in the middle approach, you're done. And 7 is just 1 and 7. Just again, we only have a few minutes, so I'll go ahead and write them down. You get 1 and 1/7, 2 and 2/7, 4 and 4/7, 5 and 5/7. If I could write, that would help. 10 and 10/7, 20 and 20/7. Notice this gives us a list of 24 possibilities. That's a lot, right? We don't want to check all 24. That's crazy. You're lucky you have graphing devices nowadays. When I was a student, back in my day, we didn't have graphing devices. We had to do it by hand. None of you care, I'm sure. Okay, boomer. All right, anyway. I'm not a boomer. But anyway, let's look at this one. 7x to the 5th minus 37x to the 4th plus 59x cubed plus 7x squared minus 76x plus 20. How many roots did we say we need to find? 3. How many do we see on the screen right now? I see 3. Hopefully they're in my list, right? This one is -1. That's a good one. This one is 2. This one is, well, I recognize that decimal. 0.28571 is about 2/7. Okay? So those would be the ones I would check first. I would check negative. Actually, I would do -1 and I would do 2 first before you start playing with the fraction. Okay? So for that one, I would go back over here from the graph. I would check -1, 2, and then check your 2/7. Only because I would rather do the fraction as little as possible, right? If you start with a 2/7, then I got to do that all the way through the 5th degree polynomial. If I wait till here, then I only have to do it for the 3rd degree polynomial. All right. Before you head out, I want to make sure I give you your review sheet. Or one of the review sheets. There's another one on Moodle as well. Oops, sorry. Just kick something. Your umbrella, is that what I did? Something. complex roots on Wednesday. Well, we can start with some complex roots. We'll do some of those examples on Wednesday. So work on these extra ones that are in the packet for practice. Make sure that you're comfortable doing those, because we're going to build on that on Wednesday. Okay. Have a good one. We will see you then.